couple of students last summer from India, undergraduates, to design a new space colony. The idea was to improve somewhat on the designs that we have seen from the 70s and also the design that I did in the 80s. Next slide, please. A couple quick acknowledgments. Dr. Kapana used to work in the office next to mine. She was incinerated in the space shuttle Columbia as it came back. And we worked together a little bit, nothing particularly major, but I'm hoping that the name survives, even if none of the design decision does. Next slide, please. If you want to live in space, and then you want to live for more than a few minutes, you need air at reasonable temperatures. So we all know that. If you want to live for more than a couple days or a couple of weeks, you need water and food, which means you need agriculture. If you want to live and not get cancer for more than a few decades, you need radiation protection, and that implies shielding mass. And the reason that it's in color is this is a driver, one of the major drivers of the system, probably the major driver. We assume for this study 10 tons per square meter of surface area of the habitat. Some people will say that it only takes 5 tons, and then you can cut all my numbers in half. So much better. But 10 tons is the amount of atmosphere you have over your head right now, and that doesn't even count the fact that we get protection from the Van Allen belts.
Your microphone is on the phone.
Oh well, let's hold it. Children. This is not brought up, but if you want to live for more than one generation in your space colony, you must have children, right? I mean, a little obvious, but it gets missed a lot. And it turns out that's a huge driver of where the colony goes. And the last thing is colonization is a real estate business. What you're selling is a place to live. And if it's not a nice place to live, ain't nobody going to want to live there. Next slide, please. This is what I think of as current vision. And this is really exciting. To land on another planet, to go out there, to explore, to be the first there. But when the kids are screaming and the baby just put another stinky diaper out and your spouse is headed up to here with your bright idea to go into space, you do not want to be in a 20-meter tin can. I can assure you. Next slide. You want to be someplace like this, which is incredibly dark. That's just the way, if anybody can turn down the lights a little bit, that'd be helpful. But if you can see it, this is a Stanford torus. It's 6 kilometers around. So the baby's stinky diaper will get diffused fairly quickly, although you're going to have to pick it up. Because if there's a lot of those diapers, it's the whole colony will get stinky. And your wife or your better half can take a walk when she needs to. Or alternately, next slide please, you might want to live here, which is the O'Neill colony. The whole point is you cannot, if you want to live there, if you want to raise your children there, it's got to be big and it's got to be nice. Next slide please. And that means, along with the children requirement, it's going to be in orbit. I like to be a little controversial. If you want to raise strong children, and what I mean by strong children is not going pumping iron. I mean children that can walk around on Earth. Okay? You must raise them in 1G. We do not know what's going to happen to children who are raised in 1/3 G or 1/6 G in the moon or Mars, but we know for sure that they will have weak muscles and they will have weak bones. And if they get an all-expense-paid scholarship to Harvard, they will not be able to go. If they're an Olympic-class athlete, they will not be able to go. If they're a world-class musician, they will not be able to tour the Earth. If you raise children in this environment on Earth, Child Protective Services would take them away from you. It's child abuse. So the first colonies have to be at 1G, and that means they have to be in orbit. In order to get 1G in orbit, of course, you've got to rotate. We assume for this study that 2 RPM is the maximum that people can tolerate, which implies a 250-meter radius. Turns out this is a huge system driver because the mass of the colony is the inverse of the 4th power of this. So if this number is really 1, you're going to pay 16 times the mass in the colony. If this number is really 3, you can cut it down by a factor of 16.
Go to 5.
Then
your children will really get into Stanford.
At 5, that actually gets too small, and there's some data that say that 3 is the best we can do. Not the greatest data, but data. There's a couple of minor advantages to being in orbit. You get continuous solar energy without 1,000-kilometer railroads. Large-scale construction should be a lot easier in zero-G. Short supply lines to Earth. Moon's not too bad for supply lines to Earth. Mars is terrible, right? Greater growth potential. You put the Earth, the Moon, and Mars together, you get about the surface area of the Earth. Give or take a bit. If you take, one of the larger asteroids, tear it apart, remember that's a 3D structure, and turn it into 2D shells, that's your pressure vessel plus radiation shielding, you get at least 100x, 100 times the surface area of the Earth, and some people would claim 1,000. That's a lot of growth. Okay? There is, however, an enormous disadvantage to orbit. The total materials available in orbit today is on the order of a couple of atoms per cubic centimeter, which is a little shy of the 15 million tons that pulp-in-1 weighs. Now, the people that tell you that orbital colonies require billions of tons of material, and they're wrong by about 2 or 3 orders of magnitude. Next slide, please. Some of the earlier colonies. This is the Bernal sphere. It's a relatively new computer model of it. This is the habitat. It's spherical. It's actually a slightly elongated cylinder. There's a crystal palace of tori they give you for agriculture. They're less shielded. These are mirrors to get sunlight in. But it has a couple of problems. First of all, spheres in general use more shielding than you need for a given living area. And the second is, this is rotationally unstable. This system's supposed to rotate about this axis. But if you just look at it, you can see that the maximum angular moment of inertia is in this direction. And in a perturbed environment, over time, any system will rotate around the axis with the greatest angular momentum. A moment of inertia, and that's not the one you want here. Next slide, please. This is O'Neill's cylinder. It has that same rotational instability. It's also, I've never really been fond of these large external mirrors. Next slide, please. This is the Stanford torus. This is rotationally stable. That's good. As we'll see in a minute, any torus has an excessive amount of shielding mass for a given living area. I've never been a fond of this big mirror here because it's, if you screw up, you're going to intersect the colony. That'd be bad. The other thing is this has a stationary shielding, and then a couple of meters away, you've got your rotating colony at 100 miles an hour or whatever, and if you screw that up, you're all dead. That's bad. Next slide, please. This is Lewis 1. Did this in the early 90s. There's a shuttle orbiter there for scale. This is also rotationally unstable. Like the others, this is a solar array. It has a completely inadequate power supply. Has a little better thermal rejection than some of the other ones, although in the Stanford torus they actually have good thermal rejection, just not the picture. So it's rotationally unstable. It has no natural sunlight, as the others do, which is not horrible, but it's not the greatest either. And it's got that same problem with the Stanford torus of the stationary shielding and the rotating habitat. Next slide, please. So here's why cylinders are the best colonies. If what you're trying to do is minimize the total mass for a given amount of living area, 1G. So I'll define a term, which I hate to do, but necessary, is the shielding mass to the living area ratio. The assumption here is the living area is the 1G area. Shielding mass is proportional to the surface area, 10 times per square meter. For a sphere, if you have a 250 meter radius to rotate at 2 RPM, you get one line of 1G. So your S2LR is infinite. Now in practice, when you don't do that, you bring the surface in, and what do you get? You end up with a cylinder with instead of putting the shielding right against the wall, you curve it out, so it's clearly inefficient. For a torus, if you have a circular cross-section, and you get the best 1G area you can, which is the diameter, the ratio of the surface area to the living area is pi. You can do a little better if instead of doing a circular area, you do a rectangular area, but then your S2R is a little greater than 2. Dumbbell, you get cream no matter what you do. Cylinder, it turns out for rotationally stable cylinder, S2R is about 1.45. The net result is for the same living area, cylinder requires millions of tons less shielding. The reason that the people in the 70s went with the torus is they assumed 1 RPM, which requires nearly a kilometer radius, which means that a cylinder would just be absolutely enormous and it's like hundreds of millions of tons and you can't live with it. But if you can go to 2 RPM, you're in better shape. Next one, please. Okay, so why is a cylinder 1.45? It seems like an odd number. I mean, if the cylinder is infinitely long, S2LR is 1. Obviously, you can't get infinite, but you get it very long, you make it value S2R. But remember that argument about the rotation. In a perfect space environment, you get your rotation during range, cool, but we don't get it. We don't get that. We've got solar pressure, we've got a lumpy gravitational field from the Earth, we've got an even lumpier gravitational field from the Moon. Jupiter comes by every once in a while. So over time, unless you have active control, which is probably a bad idea for this kind of stability issues, you're going to rotate around the wrong axis if your angular moment of inertia isn't right. We know from decades of spin-stabilized spacecraft that you want, rule of thumb, about a factor of 1.2 in your angular moment of inertia. And if you work out the math, and we didn't make any mistakes, the net result is your cylinder length for a flat cap cylinder has to be less than 2.6 radius. Kapana 1 needs curved end caps because it is a pressure vessel. So we chose a length of 550 meters, which is 2.2 times the radius. Next slide, please. So here's Kapana 1, which fortunately isn't quite as dark as some of the other ones. It's a fairly squat cylinder. Here's our length and our radius. For power, we put body-mounted solar cells on the body, which is completely insufficient for operations, but it does give you emergency power. There's been a little argument on space settlers use lists lately that maybe we should use light pipes instead. So it turns out the surface area is just about big enough to take care of your agriculture. A trade study needs to be done. Over the top of this, you put a body-mounted rectenna, and you have a couple of solar power satellites that supply power. I'll have a slide on that in just a minute. In order to, for shielding, we put the shielding in the inside of the hull, so that eliminates that failure mode. It means your hull's got to be a lot stronger. Preliminary analysis suggests, there's a paper in the AIAA about this, that about 15 centimeters of steel will do the job, which is a lot of steel. Fortunately, there's a lot of iron in the moon. The size of this thing, this direction's 1/2 kilometer. Going around is about 1.5 kilometers. That turns out to be pretty close to half the size of Capitola, California, which is where I live, which is a great place to live. It's got a nice density. So half the size of my town would be 5,000 people, so that's where we came up with 5,000. And it meets the criteria that you see in the earlier studies. In order to supply natural sunlight, we go with transparent end caps. This may be a bit of a problem for various reasons, but there's ways to reinforce that brittle glass. You need a lot of glass for radiation protection. We'll have a slide on that in just a minute. And next slide, please. So the simple sunlight. If you either make the end caps transparent or use the chevron design that the O'Neill folks came up in the 70s, then you may need to filter if it's excess, but probably the glass is so thick that's not a big problem. If you put either coatings or use the glass to scatter or reflect the sunlight into the interior, you end up with continuous sunlight. Now, we're all used to the day-night cycle, blah, 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 but if you lived in Alaska or Finland or southern Chile, in the summer you have continuous sunlight, and people have been doing that for thousands of years. That must be okay. I've talked to a few folks who live there. They say it's great. A little tiring after a while. And, I forgot. I go back to the previous slide. There's one thing I forgot to mention. The thermal design is a set of radiators in a disk around. There's other possible designs. And then if you align Kapana 1, this axis with the north-south axis of the solar system, and then you can have short shades, which will keep this from interacting with the sun. Next slide, please. And next one. So thermal requirements. We assume 10 kilowatts per person for general use. That's the use in the U.S., which includes industrial, which is not an issue in Kapana 1. That's a separate set of power. It turns out that the rule of thumb for high-intensity agriculture is about 50 kilowatts per person, about 50 square meters, interestingly. The body-mounted can't possibly get you that, but 250 megawatt solar power satellites beaming from both sides will give you a density on the surface of about 400 watts per meter cubed. That's about a third of sunlight in the Earth. I'm not an expert in the antenna field, but I think that should handle it. And here's some of the assumptions on the thermal analysis. Next slide, please. Home maintenance. If you build a gadget, you got to maintain it. That's the way it is. The first problem we looked at was wobble control. As stuff moves around the inside of the colony, it's going to wobble. That's a fact. You need to deal with it. One approach is put some computer-controlled winches in the outside, attach cables with big weights, let them in and out to compensate for the weight. This would be, to work out where you should put them in the control aisle would be a great student thesis. I've heard some students take that up, and I'd love to work with them. For exterior hull maintenance, remember this thing is rotating, it's got 1G. If you have astronauts out there trying to work on it and they should make the mistake of letting go, they're gone, and they aren't coming back. We're going to have to do it with robots. Can't use people. And we have a very simple design for keeping the robots from doing the same thing that people would do. Because remember, we got these solar cell panels on the outside. If we reinforce the sides and put a structural member through here and a couple of wheels that can rotate under here, then the robot is held to the surface no matter what you do. Next slide, please. This is the interior. This is actually the interior of Lewis 1, but it uses the same idea. We haven't had a chance to do the interior of Kapana 1. The great thing about a cylinder is you got a lot of interior space and there's ways to take advantage of it. The disadvantage people have pointed out of the cylinder is if you're sunbathing up here, this is a cutaway, your neighbor down here is only 500 meters away with a pair of binoculars can have a pretty good view of what you're doing. But if you put some internal cylinders in the middle, then you block that view and you get a lot of extra living space. Now, this design was set up so that, I think it was 1/6G at the first cylinder so that any agriculture you developed would also work on the moon. You could adjust it for 1/3 if you wanted. For the Kapana 1 paper, we put the first one 100 meters out and then every 7 meters for 11 internal cylinders. And it turns out that gives us about 5 times the surface area of the exterior, which is important because remember, we want this thing to be big because we're going to live in it. We're not just going to go and work for a couple of months or a year, something like that. This also brings up the issue of how one might deal with solar storms. Now, the radiation on the external is basically designed to handle cosmic rays. And the assumption from the studies in the 70s was if you could get less than 25 rams per solar storm, that would be cool. I don't really want my pregnant wife to absorb 25 rams. I think that would be a bad thing. So we need some sort of storm shelter. The traditional way of thinking about this is everybody crams into a lead-lined box and is totally miserable for a few hours, but you can tolerate it. There is an easier way. Heppenheimer suggested making a cylindrical swimming pool around the axis of rotation. And you can do some fun things like dive straight up, and you can race you don't have to do any racing turns, which would have been great for me because I was a pretty fast swimmer in high school, but I couldn't do the racing turns, so I couldn't make the team. That's a minor point, but it's important to me. But more important is water absorbs radiation quite well. So what does a colony do during a solar storm? Everybody goes swimming. That's a lot better than being in a lead-lined box. Next slide, please. So it is my belief that the task before us as humanity, the greatest task that we have to do, and I'm sure most people here actually share this, is the colonization of the solar system. One of the things it can do, among others, being parochial for the moment, is allow the U.S. to resume territorial expansion, which we probably basically ended when Hawaii and Alaska became states in 1960. Now we have this military all over the place, but that's no substitute for territorial expansion. As we saw, with orbital colonies, we've got 100x the size of the Earth. We can expand, and everybody else can expand for a long time. We're going to be fine. We don't have to get in each other's way. The benefits are absolutely enormous. They are vastly in excess of military control of the Persian Gulf. For reasons I described, I believe the first colonies will be orbital. When I say a colony, I mean a place where you raise your kids. If you're talking about a place you go to work, even for 10 years, different issues. And Kapana 1 solves some of the problems of the early designs. There's lots of other problems for anybody that wants to work on it. Thank you very much. If there's any questions, I'd be happy to ask them. And if you don't want to ask questions and go eat, that's great too.
And what's your time frame?
Well, I as far as I know, I've worked with the only space settlement program at NASA, which has funded a grand total last year of $3,000. It's a space settlement design contest at NASA Nature Research Center. At that rate, the answer is never. The less glib answer is that if we were serious about doing something like this, there's a whole bunch of stuff that needs to be developed. We need the lunar systems that you're talking about, or something very much like it for asteroid mining. We need, you know, much cheaper launch, the sorts of things that the space dev guy. It's going to take decades just to get ready to start. Once we start, I think it's at least a couple of decades of work to build the first one.
The calculation was that your pressure vessel was about 100 multinational products worth of launch.
You can't launch it from here. Impossible. You'd have to get it from the moon to Mars. Yeah.
Have you considered some of the near-Earth asteroids as resources?
Yeah, I think my personal opinion is near-Earth asteroids are better resources than the moon, but I think that's a great competition.
It turns out that if you're working robotically, you can get your robots out there, start your processes, and basically you can get your materials, your raw materials started. And every time the near-Earth object comes close enough, you can start pulling some of the materials off. A lot less expensive from a material transfer standpoint than trying to get stuff off the moon.
This sounds like something you study.
I do a lot of reading.
Yeah. Yeah.
I don't know how many people are familiar with the work of Peter Cook. But the thing is, he's got this idea for years, and I think it's starting to develop now, that he wants to be able to create a facility where people can actually do in a lunar type environment to develop the technologies that we need to go up there. We do a lot of stuff in either companies or colleges, but the thing is, you don't do it in a cave or something to do some of these things. And the thing is, he wants to do something. Like the Mars Society's got their hab out there, which is a completely ridiculous design because of radiation. But the thing is, he wants to do something like that. And he wants, by the way, I need all your cards. I'll turn them over to him. And the thing is, he'd like to work with all these people and see what we can come up with.
Why is a centrifuge not practical in
Well, it's 250-meter radius centrifuge at 2 RPM. It's a little tricky to build. And you still get the 1.6 G towards the moon, so you have a lot of engineering problems there. Also, if you want to make it, 500 meters long, that's quite a construction project on a 1 G planet. Now, granted, you do have materials right there. But maybe you could somehow do it by angling things. It's possible. I haven't looked into that. Yeah?
You talk about it's not possible to raise children on the moon and have to go to Harvard. There's not much indication that that's true. Yeah, for example, you have astronauts that spend a year in space and Soyuz or something. They come back and it's difficult, but they readapt.
These are people who are raised from...
That's true. But people that I know that move, for example, to 12,000 feet, they adapt.
There's no gravitational difference.
That's true. But I think you're underestimating the adaptability of human organisms.
Bed rest is a pretty good approximation.
Well, no, that's
in some ways.
That's going to zero G.
No. No, here's the thing is, we know that muscles and bone develop by being stressed. That's a fact. We know that.
You'd assume if you're going to be on the moon, you're probably going to be exercising.
What's that?
Probably.
Yeah, 1.6 G is a tiny fraction. I mean, if I was to go, I weigh 160 pounds. If I was to move to something that was 6 Gs, I couldn't stand up. As a matter of fact, my heart would probably fail immediately. Right? Our bodies are adaptive systems. They adapt to the environment. Now, maybe we would get incredibly lucky and the children would be okay. But what's the chance of that? Are you going to experiment with your kids? I can experiment with mine.
No, I experiment with my baby pigs, for example.
Yeah, well, definitely. And the minimum, we should fly the centrifuge on station. You get a little data, right? But that doesn't even work.
Yeah, we don't know how much deviation from the normal bodies of stand.
I think getting animals on the moon, soon is important.
We shouldn't assume those problems now. We have to find out what they are.
It would be much better to have this
discussions whether muscle loss is neurological or physiological. Russians and some Europeans think it's mostly neurological. We think it's physiological because we are meatheads.
But that's adults.
Yeah, but you
Children
shouldn't
aren't the
assume,
same.
you should not design now systems for answers which we don't know yet. I mean, it's not a criticism, you know, but one should, you know, I think one has to spend a lot of time on the moon and then we find out who's right and who's wrong, and we don't know.
But it's kind of all, it's just like the first shuttle flight. Who's going to raise their kids in 1/3 G? And who will allow, you know, what society would allow children to be subjected to that kind of experiment?
But the ones who don't, will never make it, so that's the answer.
That's true.
Yeah.
Well, just wondering, is it any harder to worry about with a centrifuge on the moon, any harder to worry about the 1G factor than it is having to worry about Coriolis and any other spinning thing?
Well, there's a little bit of data on people's reaction to spinning. And that data says that 3G is okay, as long as you don't change, you know, go back and
The
forth.
diameter is important.
Yeah, well, for 3G, well, you notice I chose 2G. I mean, 2 RPM, 2 RPM, which is rather than 3 RPM. Because 3 RPM, you get a pretty small system.
It's nothing to do with G, I mean, it's the diameter.
Right, but if you're going for 1G, the rotation rate determines the diameter. So if you're at 3 RPM, you get 110 meters. If you're 2 RPM, you get 250. If you're at 1 RPM, you get 890 meters.
Well, why are you getting away with 2 versus 1 of 30 years ago?
If you read, I mean, the interesting thing about all that stuff in those studies, first of all, they don't give you any of the references on, you know, where they got this data. The second one is the data says that they cite says 3G, but they assume that people would be moving between 0G and 1G very often, and that's what would drive them to 1G. They didn't provide any of the data, so I have no idea what the basis was. So I think the number is somewhere between 1 and 3G. If it turns out to be 1G, if it turns out to be RPM, sorry. If it turns out to be 1 RPM, I don't get my children's names right either sometimes. If it turns out to be 1 RPM, the first colony can't be a cylinder, it's just too big. And then that's why they went to the Stanford test. You've had a question for a long time.
Yes. What about chemical, DNA, to artificially cause bones?
We have absolutely no idea.
I wouldn't.
My sister does gravitational bone research. I know, I just picked up a few of things. Yeah.
Back in the early 80s, I worked on a program where we did some calculations on the idea of a large centrifuge on the moon. Basically, the idea was you made a railroad track around the inside of a small crater, and you put basically a train load of cylinders on this thing, ran around this, and you could live in this. The problem is it worth the cost? And the answer is no.
Yeah, I would think it'd be difficult to build something big enough that you would want to live in. And plus you have to expend energy to constantly keep the site running around.
Yeah, well,
Not to mention wear and tear.
yeah,
Yeah, and maintain this, I don't like active systems.
yeah.
You know, active systems screw up. You want the physics to work for you.
And chances of catastrophic failure go
Well,
over the whole system
Yeah.
basically.
You want to run these things for generations. Any probably failure mode is probability 1, right?
We probably should continue our discussion over there.
Thank you all.